Hi there, and welcome to NASA's Goddard Space Flight Center in Greenbelt, Maryland, home to the nation's largest organization of scientists, engineers, and technologists.
Our work encompasses the core disciplines of Earth science, planetary science, heliophysics, which is the study of sun and space weather, and astrophysics, which covers the whole cosmos. These lines of businesses have helped guide the success of several notable missions, including the Hubble Space Telescope, the Mars Atmosphere and Volatile Evolution mission, OSIRIS-REx, which is on its way back to Earth with a sample of an asteroid, and a host of other satellites that monitor Earth, our changing climate, and the dynamic universe.
My name is Travis Warab, and I'm an engagement officer here at Goddard.
And I'm Courtney Lee, a video producer here at the Flight Center. Our campus at Greenbelt contains 34 buildings over 1,200 acres, which translates to over 3 million square feet of research space. But Goddard consists of more than just a Greenbelt campus. We have 5 other locations: the Wallops Flight Facility in Virginia, the Goddard Institute for Space Studies in New York, the Katherine Johnson Independent Verification and Validation Facility in West Virginia, the Columbia Scientific Balloon Facility in Texas, and the White Sands Complex in New Mexico.
Today we're going to take a tour of some of our facilities. A substantial amount of work is required to get a mission off the ground. Goddard is unique in that every element of a mission can be facilitated here, from designing, manufacturing, launching, controlling, and ultimately gathering and analyzing data. This NASA facility is a one-stop shop.
Our first stop is at the Visitor Center, where everyone can come and learn about what we do. From strolling through our rocket gardens to immersing yourself in our solarium, which explores our sun through art and technology. The Visitor Center has multiple interactive exhibits for people to learn more about Goddard's research.
But the Visitor Center isn't the only place where you can see our research on display.
We're going to take you behind the gates on an exclusive tour of our facilities.
Come on, let's go.
Before any mission becomes reality, it goes through several stages of development and planning. At Building 34, scientists think of problems that need to be solved and get funding to develop practical solutions. For example, the employees at the Sample Analysis at Mars Suite Investigation, also known as SAM, examine the habitability of Mars.
I'm here at the SAM lab, and as you can see, it's quite a tight space due to the temporary clean tent. But every day, scientists conduct experiments and investigations to determine if ancient Mars provided a habitable environment where microbial life might have thrived. SAM was built on mass spectrometer technologies that have been developed to explore the atmospheres of Jupiter, Venus, and Saturn's moon Titan. In addition to measuring atmospheric gases, SAM also measures gases released from rocks and soils on Mars. Let's hear more about SAM from the SAM Deputy Principal Investigator, Charles Mailspin.
Here we have the SAM testbed, which is an exact working replica of SAM, which is located in the Curiosity rover on Gale Crater, Mars. SAM took about 7 years to complete, from a proposal in 2004 to a 2011 launch, and required 150 people in its creation. After landing on Mars in August of 2012, it is still operating on the surface after 8.5 years. Goddard scientists and engineers solved problems that arose as SAM was being developed. For example, when the company that was providing the 52 microvalves in SAM went out of business, Goddard stepped up to reinvent the valves, which are still being used in missions today. In another situation, the turbomolecular pumps weren't reaching their planned lifetimes. A Goddard team worked with the commercial provider to redesign the pumps, and they are still operating on Mars. With SAM and other missions, we focus on solving problems to create instruments that will help answer the questions we have about the universe beyond our planet.
Thank you, Charles. With missions like SAM and others, we implement a project lifecycle, where we use scientific findings from current missions to develop new missions. We head to the Planetary Environments Laboratory, where a new spacecraft element is being developed.
The Planetary Environments Laboratory studies the atmospheres and surfaces of planetary bodies. Scientists there participate in all phases of planetary investigation, from developing instruments to analyzing data sent back to us from spacecraft.
The Planetary Environments Laboratory is home to a key instrument on Dragonfly, a rotorcraft scheduled to land on Titan, which is Saturn's largest moon, in 2034. The team is currently working to design every detail of the craft and the instruments on its scientific payload. Here with us is project lead Dr. Melissa Trainer, who will tell us more about Dragonfly.
Well, we've already presented the mission concept to the rest of NASA. Now our engineering team is hard at work, making sure we've thought through all the potential problems in the design. In this phase, it's a lot like going from an architect's sketch of a house to a blueprint where every beam and outlet are clearly marked. We end up spending a lot of time in this stage where we test prototypes and plan details because we want to get it right before we actually build the spacecraft and the instruments. An example of one design change we've experienced comes with the instrument that drills samples from the Titan's surface and how it brings them to the Dragonfly mass spectrometer, which is the instrument we're building here. At first, the delivery system was designed to look like a funnel to dump samples onto a tray. But then we realized there were a couple of problems with that model. First, Titan's samples can be sticky, especially if you warm them up compared to the Titan's surface. And it would be hard to clear them off the tray before more samples are taken. Second, the gravity on Titan is low compared to Earth, and we can't rely on the samples settling easily on the tray. So instead, we came up with a new design that catches particles from a stream into a cup and moves them into a chamber. We've also worked a detailed design where the sample chamber side stays cold, like the surface of Titan, while the mass spectrometer side stays warmer. This interface is critical to getting the best measurements of Titan's surface samples, and it has already been through testing here at Goddard. Now, our team is continuing the work to make sure that everything fits into the rotorcraft lander in a way that makes sense and allows us to accomplish our science mission at Titan.
Thanks, Melissa. Now let's head over to another part of campus, which will help us further prepare the spacecraft for launch.
Once a spacecraft component has been developed, it has to be cleared for launch in one of our clean rooms, which can range in size up to almost 37,000 cubic meters. All of this occurs in the Integration and Testing, or INT complex, which is comprised of 4 buildings. Goddard's Environmental Test, Engineering, and Integration Facility ensures every craft is space-ready by putting it through a series of high-stress tests.
Built in 1989, the Spacecraft Systems Development and Integration Facility, or SYSTIF, is the largest clean room in North America. It has an entire wall of 1,600 air filters to help protect equipment from contaminants. That means the air gets recycled every 60 to 90 seconds. To tell us more about the clean room, we're here with Delaney Burkhart, an integration engineer.
The SYSTIF clean room is like a surgeon's operating room. It prevents dirt, dust, and other contaminants from damaging spacecraft components. The largest source of this contamination is us, the personnel working on those components. To enter the room, you first must pass through an air shower, then wear a sterile bodysuit, head cover, boots, gloves, and face mask, which takes about 10 minutes to put on. Unlike a speck of dirt on a camera, a speck on a telescope lens cannot be easily removed if the spacecraft is far away studying distant stellar objects.
Once the spacecraft is built, we move on to testing, getting it ready for spaceflight conditions.
To make sure the spacecraft can withstand the sounds it might encounter during its flight, scientists test the craft in a 13-meter tall acoustic testing chamber. We're here with test engineer Yan Louis to tell us more about how the chamber works.
In this chamber here, our scientists use altering flows of gaseous nitrogen to produce sounds as high as 150 decibels. In other words, 20 decibels louder than the roar of a jet engine. Using 6-foot speakers, the sound is blared in a 2-minute test to make sure instruments can withstand such noises.
After the acoustics test, we need to replicate the conditions the craft might encounter in space, which is right around the corner. The Space Environment Simulator, operational since 1962, is a thermal vacuum chamber designed to expose spacecraft components to spaceflight conditions. But what do those conditions look like? We're talking about an almost 400-degree temperature range, from negative 233 degrees Celsius to 150 degrees Celsius. The range is achieved by passing liquids through thermal shrouds for cold temperatures or using thermal lamps for high temperatures.
Our simulator is roughly 12 meters tall and 8 meters across. It operates with massive mechanical vacuum pumps, which are like huge versions of the vacuum cleaners people use at home. We have cryopumps to condense remaining gases out of the chamber. The mechanical pumps and the cryopumps work together to eliminate almost all of the air in the chamber. You wouldn't want to be inside while that's happening. It is just a billionth of Earth's normal atmospheric pressure. It takes up to 12 hours to pump the chamber down to that pressure and 2 to 4 days to go back to room temperature.
And we're not done yet.
Next, the instruments get tested in the high-capacity centrifuge. Built in 1965, this used to be an all-in-one machine. It's not designed for astronauts. However, it used to be able to test environmental, vibration, acoustic, and G-force conditions. As our spacecraft grew in size, it had to be modified.
The centrifuge now only simulates the acceleration level of a rocket during the launch phase, typically about 10 Gs. This allows scientists to see how stress affects a craft's structures and verify that it can withstand launch. It can rotate at 155 miles per hour. Our test limit is 30 Gs, or 30 times the gravity we have on Earth. The centrifuge draws 1 gigawatt of electricity, and when in use, generates 200 mile per hour winds. It's been used for more than just spacecraft testing. In 2002, NASA partnered with the NTSB to test SUVs and analyze the tipping point for manufactured models.
Once a spacecraft has passed all testing phases, it's go for launch.
For many Goddard launches, we head to the beaches of Virginia. Wallops Flight Facility is NASA's only owned and operated launch range for a variety of vehicles, including research aircraft, sounding rockets, scientific balloons, orbital vehicles, and unmanned aerial vehicles. It's America's oldest continuously operating rocket range, with launch operations dating back to the summer of 1945.
Wallops provides low-cost opportunities to conduct scientific experiments and for engineers to test their technologies ahead of their main missions. Many services support these tests, including integration and testing facilities, launchers and runways, as well as tracking and data services. Let's head to the launch viewing area, where Sam Henry is going to tell us more about the launch cycle.
There are many moving parts that go into a mission, so everything can come together on launch day. Depending on the vehicle, technicians may arrive anywhere from 4 to 8 hours ahead of T-0 to begin testing on the vehicle and support systems to make sure everything is ready. Public safety is a top priority, so we launch our rockets over the ocean. Surveillance teams will monitor boat and air traffic before the rocket can take flight. Weather also plays an important role on launch day. Meteorologists give weather updates from 72 hours until just minutes before launch, so teams can be as prepared as possible. Winds, severe weather, and cloud thickness are the biggest concerns on launch day. When conditions align, we are a go for launch and ready to safely conduct our range operations. I'll head back to the control room where Courtney and I will tell you more about other Wallops missions and responsibilities.
Wallops conducts research here on Earth, as well as in a near-space environment, looking deep into the cosmos. Wallops manages NASA's Scientific Balloon and Sounding Rockets program, which are launched not only from the flight facility in Virginia, but from areas across the globe, as far north as Norway and as south as Antarctica.
On average, we fly 10 to 20 scientific balloon launches each year. These platforms allow researchers a chance to gather data with flights in the stratosphere, a near-space environment. Flights can run up to weeks at a time, depending on science mission requirements. Sounding rockets are manufactured, tested, and launched from Wallops in remote locations. Many of these technology missions we support end up being integral to larger missions, like Artemis. With around 20 missions a year, the Sounding Rocket program is one of Wallops' most active platforms. We also open our facilities to industries for space and aeronautics research. In the past 25 years, we've collaborated with over 50 established and emerging aerospace companies. We also support other government agencies with their tests, missions, and training exercises. We look forward to partnering with these groups and others in coming years.
As you can see, Wallops provides a large range of options when it comes to testing equipment or conducting near-Earth research.
And you can often watch the launches online and join in on the action.
Once the vehicle has been launched, we jet back to Goddard to run communications with the craft.
When the craft is finally in space, how do we communicate with it? Goddard has over 60 years of communications and navigation support going back to the Mercury, Gemini, and Apollo eras. Goddard's Near Space Network coordinates all space-to-ground communications for missions near Earth.
The Near Space Network enables missions to send back significant amounts of data for investigation and discovery. These include missions like the Hubble Space Telescope and the International Space Station. In fact, the network plays a crucial role in NASA's human space exploration effort. It provides the International Space Station with constant communications, letting astronauts working and living there to always have a connection back home. We are here with Rosa Avalos-Warren, a human spaceflight mission manager, to tell us more about the Near Space Network.
Goddard's Exploration and Space Communication Division oversees the Near Space Network. The network blends commercial providers and government assets to support missions from Earth's orbit up to 2 million kilometers away. These missions include launch vehicles, robotics and science satellites, technology demonstrations, and human spaceflight missions. To communicate with astronauts and spacecrafts, we download signals from satellites and translate them into recognizable data. This data ensures mission success for NASA.
The network is involved in a variety of missions, including NASA's Commercial Crew Program, which provides communications and navigation support to companies like SpaceX and Boeing. As we go to the moon as part of the Artemis program, the network will provide telemetry, command, and tracking support to the missions as they launch into space. In doing so, we work alongside the Jet Propulsion Laboratory's Deep Space Network. We're here with Brandon Bethune, the Deputy Project Manager for the Near Space Network, who will tell us more about some of the recent projects scientists are working on.
With missions like the Laser Communications Relay Demonstration and the Orion Artemis II Optical Communications System, we are infusing optical communications into our mission architectures. We are also advancing our radio frequency capabilities and integrating Ka-band capabilities into our network so missions can communicate more data, increasing our capacity for discovery. And that's not all. We're even implementing a delay disruption tolerant networking, which is a building block for NASA's LunaNet, a communications and navigation architecture at the moon.
Our support to both human exploration and science investigation is always evolving and adapting to the needs of missions and empowering NASA's vision.
Thanks for joining us on this tour of Goddard Space Flight Center. We've seen exhibits at the Visitor Center, explored the SAM Lab, investigated how spacecraft are tested at the INT complex, launched a rocket at Wallops Flight Facility, and coordinated communications at the Near Space Operation Control Center.
We hoped you enjoyed your tour of Goddard. If you want to learn more, you can visit our website or follow us on social media. We hope the rest of your day is out of this world.
And keep looking up.